The power of probability mathematics. Introduction. Mathematics has always been considered as an important tool for solving problems and advancing civilization. With its vast array of concepts, techniques, and methods, it has helped us to make sense of the world and understand complex systems. However, not all mathematical concepts are easy to understand, especially for individuals who struggle with mathematics. In this paper, we will focus on probability mathematics and why it is considered the most powerful and easiest form of mathematics for humans to understand. Probability mathematics, also known as probability-based mathematics, is a field of mathematics that deals with the study of uncertainty and randomness. It provides us with the tools and techniques to understand and quantify the likelihood of events and outcomes. This form of mathematics is powerful because it helps us to make decisions based on the likelihood of events and outcomes, allowing us to minimize risk and uncertainty. One of the reasons why probability mathematics is considered the easiest form of mathematics for humans to understand is because it is based on our natural inclination towards guessing. As Shafee Hussain has noted, probability mathematics can be seen as a form of probable mathematics or just guessing. This means that our brains are naturally wired to use probability-based thinking and problem-solving. Our advanced brains use probability-based mathematics to solve problems in a number of ways. For example, we use it to make predictions about future events, to make decisions based on uncertain outcomes, and to assess the likelihood of risks and benefits. By using our brain's probability-based thinking, we can improve our problem-solving skills and make better decisions. To use probability mathematics to solve problems, it is important to follow a few key steps. 1. Identify the problem and gather all relevant information. 2. Determine the outcomes and events that are relevant to the problem. 3. Assess the likelihood of each outcome or event. 4. Use the probabilities to make predictions and decisions. The proposed techniques draw on established probability theory and mathematical principles. Additionally, insights from cognitive psychology and decision science inform strategies to apply probabilistic thinking more effectively. An interdisciplinary synthesis approach allows tailored, theoretically grounded techniques. Analysis of core probabilistic problem-solving steps. 1. Identify the problem and gather information. Define the primary question and unknowns. Identify key variables influencing outcomes. Collect relevant base rate data, empirical observations, and experimental findings. Consult probability theory guides, e.g. Kolmogorov axioms, to formalize parameters. 2. Determine relevant outcomes and events, enumerate possible outcomes, hypotheses, and event chains/sequences. Eliminate logically impossible or extremely improbable outcomes if needed. Represent outcomes visually with diagrams or probability trees if helpful. 3. Assess the likelihood of outcomes/events. Leverage laws like Bayes' theorem to calculate conditional probabilities. Avoid cognitive biases like neglecting base rates or recent experiences. Update probabilities iteratively as new evidence is acquired. 4. Make optimal predictions and decisions. Determine which choices maximize expected utility using probability estimates. Recommend interventions that probabilistically yield targeted outcomes. Continuously reevaluate as new data emerges. A structured, mathematically grounded approach to uncertainty can enhance decision quality across many domains like medicine, public policy, and risk management. Further research on integrating probability theory with situation-specific variables offers promising paths to improve problem-solving where randomness and unpredictability cannot be eliminated. Here are 10 examples of probability mathematics and their use cases. 1. Bayes' theorem. Bayes' theorem is a mathematical formula that describes the relationship between prior probabilities and the likelihood of an event based on evidence. It is used in many applications, including medical diagnosis, spam filtering, and artificial intelligence. 2. Markov chain. Monte Carlo, MCMC is a computational method for generating samples from a probability distribution by using a Markov chain. It is used in many applications, including Bayesian inference, machine learning, and statistical physics. 3. Central limit theorem. The central limit theorem states that the sum of independent, identically distributed random variables approaches a normal distribution as the number of variables increases. It is used in many applications, including financial modeling and quality control. 4. Chebyshev's inequality. Chebyshev's inequality is a mathematical theorem that states that for any given distribution, at least a certain fraction of the values must lie within a certain distance from the mean. It is used in many applications, including hypothesis testing and statistical analysis. 5. Random walk. A random walk is a mathematical model that describes the movement of a random variable over time. It is used in many applications, including financial modeling, physics, and epidemiology. 6. Conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. It is used in many applications, including decision analysis and game theory. 7. Hypothesis testing. Hypothesis testing is a statistical method for testing the validity of a claim or hypothesis based on sample data. It is used in many applications, including quality control, medical research, and psychology. 8. Maximum likelihood estimation. Maximum likelihood estimation is a method for finding the values of parameters that maximize the likelihood of observing a particular dataset. It is used in many applications, including machine learning, signal processing, and finance. 9. Martingales. A martingale is a sequence of random variables where the expectation of each variable given the past is equal to the current value. It is used in many applications, including finance, gambling, and game theory. 10. Stochastic processes. A stochastic process is a random process that describes the evolution of a system over time. It is used in many applications, including physics, engineering, and economics. Once upon a time in a bustling town, there lived a curious young woman named Ada who was fascinated by the mysteries of life. Ada's day job was ordinary, working at a local store, but her mind often wandered to questions big and small. One day, Ada stumbled upon a dusty old book on probability mathematics in the attic of her childhood home. Intrigued, she began to delve into the pages and soon discovered the ease with which she could understand and apply the concepts of randomness and uncertainty. The book described probability as the study of uncertainty and randomness, providing tools to understand and quantify the likelihood of various events and outcomes. Ada was thrilled to find that this form of mathematics aligned naturally with her instinctive guessing and intuition. Excited to put her newfound knowledge to use, Ada decided to tackle some of the town's problems using probability mathematics. She started small, helping her friends make decisions based on uncertain outcomes, such as planning outdoor events considering the weather predictions. As she grew more confident, Ada decided to address a pressing issue in her community: the frequent power outages. She gathered relevant data and used probability to model different outcomes, considering various factors such as weather conditions, equipment failures, and demand surges. Ada identified the most likely causes of the power outages and suggested preventive measures. The town implemented her recommendations, and soon the power outages decreased significantly. Her success didn't stop there. Ada applied probability mathematics to diverse scenarios, from optimizing the town's supply chain to predicting and controlling the spread of flu in winter. The townspeople were astonished at how Ada could make sense of seemingly random events and improve their quality of life. Word of Ada's prowess spread, and soon she was invited to share her methodology in solving problems using probability mathematics. She explained the importance of identifying the problem, determining relevant outcomes, assessing likelihoods, and making optimal decisions based on these probabilities. Ada also shared practical examples of probability mathematics, such as Bayes' theorem, Markov chain Monte Carlo, and the central limit theorem, demonstrating their wide-ranging applications in various fields including medicine, finance, and public policy. In the end, Ada's journey illuminated the power and simplicity of probability mathematics, not just as an academic pursuit, but as a practical tool for problem-solving and advancing civilization. The townspeople came to realize that, armed with the wisdom of probability, they could navigate the uncertainties of life with greater confidence and precision. And so, Ada's story became a testament to the power of probability mathematics. The tale concluded with a gentle reminder: while we may not be able to predict winning the lottery, the knowledge of probability can empower us to face the uncertainties of life with a smile, knowing that enlightenment is our most valuable ally in the quest for understanding our complex world. Will you win the lottery using this research data? No, and you are more likely to be hit by a nuclear missile while sitting on the toilet probability. Check out researchforum.online for the full research paper.